Hello, everyone, and welcome. My name is Rula Adib. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of Certip and ESTCP. Today's event focuses on DoD-funded research to advance the cometabolic remediation of both traditional and emerging contaminants. The webinar will feature one speaker, Dr. Paul Hatzinger from Acton Federal Services. Paul will discuss the fundamentals of cometabolic processes and also provide examples of successful field applications. He will pause halfway during his presentation to answer questions, and we will conclude the webinar with a longer Q&A session. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provided to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you continue to have difficulties or if your screen freezes, just try keying in Control and F5 to perform a hard refresh. If you're accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear in your screen. If you experience difficulties with the audio, one option is to call into the conference line. The number and required webinar ID are shown here, and where they were also provided to you in your webinar registration confirmation email. Please use the chat box for comments related to technical difficulties. You are always free to send us a chat if you continue to have problems, but do not use the Q&A function to submit any issues related to technical difficulties. You can also download a PDF of the slides at the link shown here and call into the conference line provided to you in your confirmation email. A link to the slides is also provided to you in the chat box. Keep in mind that a final option to view the webinar is to join the live stream on the Certip and ESTCP YouTube channel, and that link is shown here. One last reminder, today's broadcast will be listen only. Submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. We do encourage you to submit them well in advance of the Q&A questions. And when you do submit your question, please make sure to add your organization name at the end of the question so that we can identify you during the Q&A sessions. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of Certip and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Andrea has been with Certip and ESTCP since 2001, and before that, she was a research leader at the Battelle Memorial Institute, where she conducted scientific research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thanks so much, Rula, and thank you to everyone who's here today to hear our webinar. I know you are all here to hear Paul Hatzinger, and I don't blame you. He's a great speaker. But before we get to Paul, let me give you just a brief introduction about who we are before we get started. This webinar is sponsored by Certip and ESTCP, which are the DoD's environmental technology programs. These are companion programs, and Certip is our science and technology program, or really a traditional R&D program. And then ESTCP is our demonstration and validation program. We work very closely with these two programs, and what we typically see is the research that's developed under Certip as it matures and is ready to progress. We will move it into ESTCP for further testing and demonstration in the field. And the idea is to bridge that gap between research efforts and really full-scale application so that we have that data at a field scale so that it leads to acceleration of commercialization or broader adoption of those technologies. The drivers for our work are several. It's a very broad program. First is the sustainment of the testing and training ranges, as well as our facilities and operations. And as you can imagine, this is quite broad. It can range from anything to maritime sustainability, dealing with threatened and endangered species, noise issues, munitions constituents, and a host of other issues. We also address reduction of current and future liability. And we look at that in two ways. One is through a traditional pollution prevention program where we're looking to eliminate pollutants or hazardous processes from the manufacturing, maintenance, operation on the installations. And then we also look to deal with contamination from our past practices. That can be chemicals of concern in groundwater, soils, or sediments, as well as any emerging chemicals of concern, and dealing with our large unexploded ordnance liability. So this all drives the sort of research we fund. We have these main focus areas, particularly high on the list has been PFAS and AFFF. We're also dealing with installation restoration, installation resilience, munitions remediation, sustainable energetics, corrosion and repair technologies, and electrical infrastructure and planning. And the presentation that you'll hear today falls under this installation restoration area. Always important to us is our technology transfer. Everything we fund is available on the web. Either when it's in progress, it will be at least a brief description of what's going on with the project. And then as the project matures, we are developing different technology transition products, which can take the form of many guidances, manuals for how-to on different technologies are developed, in-person training videos, and then ultimately it is this webinar series that is also a key component of our technology transfer efforts. Listed here are some of the upcoming webinars in our series, and you can see the topics are widely variable, so you should easily be able to find something of interest to you. To register for these webinars, you can go to this link, and the registration is open quite early for all of the webinars so that you can get it on your calendar. In addition, we also archive everything we've done on these webinars. So you can also go to the site, you can see past topics, and you can listen to the webinar again if you missed the current one. So at this time, I'd like to turn it back to Rula to introduce our next speaker.
Thank you, Andrea. It is my absolute pleasure to introduce today's speaker, Dr. Paul Hatzinger, who is the Director of the Biotechnology Development and Applications Group at Aptum. Throughout his 25-year career in research and development, Paul has studied cometabolism of traditional and emerging DoD contaminants. His research group at Aptum has been instrumental in improving understanding of degradation processes and developing field approaches to utilize these processes for contaminant remediation. Paul has authored more than 90 peer-reviewed papers and book chapters and has served as the PI on research grants from the National Science Foundation, EPA, the Department of Energy, the Air Force Civil Engineer Center, the Navy Environmental Sustainability Development to Integration Program, the Army Corps of Engineers, as well as Certip and ESTCP. And finally, Paul earned his bachelor's degree from St. Lawrence University and his master's and doctoral degrees from Cornell University. Paul, the floor is yours.
Well, thank you so much, Rula. And Andrea, thank you for the invitation to give this seminar on a topic that's near and dear to me, which is cometabolism. So what I'm going to discuss today, here's kind of an outline. I'm going to kind of give you a little background, some history, an area I call fallacies and facts. So I'm going to sort of discuss what cometabolism is and what sort of some of the perceptions are that I believe they are. I'm going to go through some field considerations and then give 3 very brief case studies. There's a lot of additional information on these cases that you can get from the Certip ESTCP websites and other seminars. We'll stop for a Q&A, and then I'm going to go into a topic that is of great interest, which is the potential for this process to contribute to natural attenuation of VOCs and 1,4-dioxane in particular, and then we'll wrap it up with a second Q&A. So I should mention that this webinar is from an ESTCP tech transfer project. This is a multifaceted project where there's training such as this. There's going to be a system video posted where we put a video together of an actual operating cometabolic system, kind of show how it's designed in the field, how it works. And the goals of all this are to look at the fundamentals, to show some different field approaches, and really to encourage the use of this technology at DoD sites, because I think it's widely underutilized and underappreciated at this point for some of the current problems that DoD is facing in terms of contamination, as I'll sort of talk about throughout this seminar. Okay, so what is it? What's cometabolism? Well, it's the transformation of a compound by a microorganism that can't use this compound as a source of energy or of any of its constituent elements, so, as a nitrogen source. Now, if we kind of look at traditional growth-linked biodegradation here on the left, typically what happens is, there'll be a compound, let's say benzene, which is contaminant, which is a primary contaminant. The organism grows on that contaminant, so it uses it as a source of biomass. It creates CO2. You get increases in population. In this case, we're talking about an aerobic process, so the organism uses oxygen as a terminal electron acceptor. So this is kind of our traditional remediation where we have a contaminant, the bacterium grows on it. But there's a secondary process called cometabolism, and in this case, there's a substrate that is not your contaminant of concern. It might be something, it's often an alkane gas like methane or propane or ethane. It can also be small ring compounds like phenol or toluene. So the organism grows on these primary substrates, again, forms biomass and carbon dioxide, so they grow using oxygen as an electron acceptor. But through sort of a fortuitous process, and often this is based upon an oxygenase enzyme, which I'll talk about a little bit further, but this enzyme has a very broad specificity, and it degrades different contaminants of concern while the organism is growing on this primary substrate. So the organism gains nothing from this process, but yet it breaks down these different contaminants. So I'm going to go into a little bit of history. So this is a table from a 1972 review article. So 1972, Richard Nixon was president. Hewlett-Packard had just introduced their first scientific calculator that had both the square root and the log function. So we're going back a really long time. And basically, starting around 1959, some scientists named Foster and Ledbetter were doing studies with a methanotroph, at that time called Pseudomonas methanica. And they noticed that while this organism could not grow on some different substrates like ethane, propane, and butane, it converted them to acids and alcohols. And that was called co-oxidation at the time. Didn't really understand what was going on. But as you kind of move further along, you see this process occurring more and more frequently. And by the late 60s, we started to get very interested in herbicides and pesticides in this. This was kind of the evolution of this remediation industry, starts with herbicides and other different types of pesticides. And what Raymond Horvath noticed in some of his work at Cornell was that some herbicides were cometabolically biodegraded and they were dechlorinated. So this was kind of the first evidence that this aerobic process could lead to dechlorination of a compound. Now, if we move forward into the 80s, there was a foundational paper by John and Barbara Wilson, and essentially they set up a column, they pushed some natural gas and oxygen through, and they saw that TCE was consumed. It was biodegraded. So this was really important because we thought at that time TCE was largely non-biodegradable. We moved down to a gentleman named Hap Pritchard at the old EPA Gulf Breeze Lab, and Hap sort of found the same thing for phenol and toluene. So organisms could grow on phenol or toluene and degrade TCE. We move into the 90s, and there's some successful field demonstrations of this process. So in the top case at Savannah River, Terry Hazen injected methane and nitrous oxide as a nitrogen source and oxygen, and was able to document the biodegradation of TCE aerobically in an aquifer. A few years later, Perry McCarty did something similar, but with phenol and toluene, and we see degradation of TCE. So we're on this path where we're looking very strongly at the aerobic degradation of chlorinated solvents as we move into the 80s and 90s. So, and then what happened? Well, what happened is a lot of the research switched to this sort of new process, new organism, which was reductive dehalogenation, which I'm sure most of you on the phone are very, very familiar with. So there's organisms who can grow anaerobically using these solvents as electron acceptors. And the field practice really became anaerobic bioremediation. We kind of forgot a lot about, these aerobic cometabolic processes. And all of this has been very effective for treating the typical site of the 90s or the 2000s, the typical chlorinated solvent site. But I think the problem definition as we move here into the 2020s has been changing pretty significantly. What I mean by that is if we go back to 20 or 30 years ago or even further, we were dealing with a lot of source areas of chlorinated solvents. So you had milligram per liter concentrations, you have anoxic conditions, you have a lot of the parent compounds. And as an industry, and through a lot of Certip ESTCP work, frankly, many, many different technologies were developed, vetted, and applied in the field. One of the key ones was certainly anaerobic bioremediation, but there were many others as well that are still in use today for these sites. But as we move forward in history, what we see is that there are still some of these sites, and I'm quite aware of that. But the problem we're having now is that we have a lot of dilute plumes. And these are dilute CVOCs, ppb concentrations, but still above MCLs. The aquifer, though, as we move down gradient, these sites can be microaerophilic or aerobic. We have some daughter products potentially from our former reductive dechlorination approaches, things like cis and vinyl chloride, as well as co-contaminants like 1,4-dioxane. The other thing that's happened, and seems like every 5 or 6 years there's a new emerging contaminant. Of course, it's PFAS now, but at one time it was 1,4-dioxane, it's NDMA, dibromoethane. There's many, many others that are also, have also come as contaminants of concern. And as we have these dilute plumes, particularly in aquifers that are aerobic, we don't have a lot of technologies to deal with that. We have pump and treat. We really, M&A is sort of the approach you'd like to use at a lot of these sites, but when you have an aerobic aquifer, that sort of throws that out the window because that's, as I'll talk about later in this seminar, that's all based on sort of reductive bioremediation, not aerobic biodegradation. Okay, so what I'm going to argue today is that really this cometabolic approach is the best for numerous COCs, and this includes dilute chlorinated solvents, as well as this whole range on the left of different compounds that you see for things like EDB and trichloropropane, NDMA, BCEE, and many, many others. And, the general characteristics of these are kind of in the same realm. They have low environmental concentrations. They have low regulatory requirements often. They're often soluble. They don't absorb well. They don't strip well, so you can't sorb them to carbon or strip them out of groundwater with an air stripper, and they're generally recalcitrant. Now, I'm going to talk a lot more about this process, but I'm going to go into this thing I call fallacies and facts. I think most people on the phone probably have some concept of cometabolism, and as I've talked to people about this process over time, there's sort of different things that come up, and one that I was in a conversation with someone on an ITRC group on 1,4-dioxane, and this was a longtime practitioner, and his view was that this process is really unlikely to be successful because of competitive inhibition, and his comment was, well, it's like a needle in a haystack. And what he meant by that is, if you're going to stimulate this process in the field, you're often adding a substrate. You're going to add something like propane or isobutane or methane. The organisms grow on that, but they use the same enzyme that they use to grow on the substrate to break down your contaminant. So the idea is if you have a whole lot of propane in the field, they're not going to be degrading your 1,4-dioxane because they're all growing on the propane. So it's sort of like, degrading this molecule is a needle in a haystack, and that's kind of this classic competitive inhibition sort of argument. But I think the fact on that is that, yes, this occurs, but it's very organism and compound dependent. These enzyme affinities vary very widely for, both your primary growth substrate as well as your contaminant. And also, maybe even more importantly, this can be very easily overcome in the field, as I'll show you in some of these field demonstrations. But I really love this figure. This is some work by Josh Sharp and Lisa Alvarez Cohen's lab about 10 years ago now. And what Josh did is he looked at two different organisms that co-metabolize NDMA. This is a very potent carcinogen. It's found at some sites through the use of liquid rocket fuels. But what Josh did is he ran an experiment where he grew these organisms and then he put them in serum bottles and he added different propane concentrations, some of which are very high. And then he looked at rates of NDMA degradation. And what he saw is for one of these organisms, he saw very potent inhibition. So your rate of NDMA degradation falls very rapidly when you add propane. But for this other organism, you could have ppm levels of propane in solution, and this organism was still rapidly degrading NDMA. So this is a case where even though you have low NDMA concentrations, basically you can have a lot of propane around and still be degrading that contaminant of concern. The other thing is when you're doing this in the field, and these are some actual data from a field site in which we were injecting propane, often you sparge these gases in cycles. And as you start to grow a microbial population, they degrade these gases very quickly to the point where, the levels are low enough that you've overcome this competitive inhibition. Well, you still have a really good active population. And this is just an example of sparging in gases. One of the things you see, in this case, this is propane, you're only getting to a little over 200 parts per billion. So the concentrations are not very high. And as you stop sparging and the organisms start degrading this, you see over the period of less than an hour, you're degrading most of what you've put in. So really your half-lives are on the order of minutes, not hours or days once you have a good population. So if you can time this right in terms of adding your gases, you can easily overcome this competitive inhibition issue. The second thing is, well, but not many organisms do this. We know of methanotrophs and propanotrophs, but it doesn't seem like it's very widespread. And that's not true at all. And in fact, there are many, many organisms. This is just a table that shows some of the different enzymes that co-metabolize different substrates. Different contaminants, some of the different substrates that they grow on, and these enzymes are now all grouped into families. And this is likely the tip of the iceberg. So we really have a lot of different potential enzymes that can be co-metabolizing different pollutants of concern. The other thing is, well, but these organisms really only express one of these oxygenases, and in fact, that's also a fallacy. And if you went back 20 years, some of the best people in this field would have argued that, yeah, it's sort of one enzyme gets induced and, that's the way this kind of works. But as we move forward over the last 10 years or so, that's really the anomaly. That's not the primary case. And in fact, a lot of these organisms have many, many different oxygenases, and they can express many of them at one time. And that becomes pretty important in terms of what's going on in the field. And here's just a nice example of this. This is a paper that Nick Coleman from University of Sydney put out a number of years ago, and this organism is called MBB4. And now that it's fairly easy to sequence things, it turns out this organism has 6 different monooxygenases. They can be expressed at the same time. Some of them can be expressed at the same time. It grows on C2 to C4 alkenes. It grows on C2 to C16 alkanes. Degrades a whole variety of different compounds, including 1,4-dioxane and a variety of different chlorinated compounds. And if we look at this figure on the right, this is some work that we did in our lab with NBB4. We grew this organism up on ethene, which is one of its substrates, and then we added it into some serum bottles with cis-DCE with or without ethene. So in this case, there was a lot of ethene in solution. There's classic competitive inhibition. It doesn't degrade cis-DCE. It will after the ethene is gone, but in the absence of ethene, it degrades it very, very readily. Now, if we look at 1,4-dioxane, this is a little bit different. So again, we grew this organism up on ethene. There's ethene in the bottles at the time, and yet it's still slowly degrading 1,4-dioxane. So just think about this scenario in terms of natural attenuation of this organisms present at a site. You could be producing ethene from reductive dechlorination up gradient. Down gradient, you have 1,4-dioxane, some ethene from the process, a little bit of oxygen, and this organism could absolutely, if it's in the aquifer, be induced and slowly degrading 1,4-dioxane as a natural attenuation process. I'll talk about that a little bit at the end of the talk, but I just kind of wanted to point that out because this is sort of a real world type of scenario that could certainly occur. So, but the other, and this often comes up with 1,4-dioxane as well. Yeah, but growth-linked metabolism is likely to be more successful, right? You know, it's sort of hard to get this cometabolism to work, and I'm going to argue that that's not the case at all, particularly when you have contaminants that are at low concentrations, because it's extremely hard to induce and maintain cells, you know, to grow when you have concentrations of things that are in the low ppb range. There's really just not enough substrate to grow densities of organisms that are required to get good degradation rates. You know, 92% of Air Force sites have basically less than 120 ppb of 1,4-dioxane, and many of them are much lower than that. So it's hard for an organism to grow on those concentrations. And, you know, lab kinetic studies, you know, show that as well. So you can achieve a high biomass. And also, you know, it's unclear how often these organisms are present in natural aquifers, these that grow on, you know, your contaminant. Now, with cometabolism, when you're practicing this in the field, you're adding the primary substrate. So you're controlling those growth kinetics by how much of that substrate you add. The other thing that's become apparent, and this was through, again, quite a bit of Certip work, is that through cometabolic processes, you can achieve some pretty low contaminant concentrations at times. And this is one example. This is an organism in our lab called ENV425. It's isolated more than 20 years ago because it degrades MTBE and lots of other things. But in this case, we were looking at this organism. We grew it on propane and then looked at its degradation of NDMA. This is 8 parts per billion, so only 8 ppb. But within 24 hours, this organism degrades that down to less than 2 parts per trillion, so 2 ppt. So you can potentially achieve very low contaminant concentrations in situ using this process. Finally, well, but it's hard to apply, right? I mean, gosh, you've got to add gases to groundwater. That's not as easy as pumping in, you know, an emulsified oil. It could be dangerous. I've heard that said, you know, and basically that's just, you know, that's just not true. We've sort of reached a point in this field where, you know, good practitioners and field engineers can apply this easily and safely. You know, everyone has a propane cylinder in their backyard on their gas grill, and you know, people aren't screaming about how dangerous that is. So, and when you have engineering controls on all of this, it's very easy to add these low concentrations of gases in the field. And there's a lot of good ways to do this. One is biosparging. So this is based upon, you know, the old process. First of all, just air sparging to strip contaminants, and then you know, just oxygen sparging in order to, you know, enhance the degradation of things like BTEX or petroleum hydrocarbons. But essentially, you sparge in your gas with oxygen or in air. Typically, you would do this in air. There's no pumping infrastructure required. You get a good radius of influence. It works in confined and unconfined conditions. You know, the negative side, you can certainly get preferential flow paths. But again, all you're doing here is adding the gas to stimulate growth of the bacteria. You're not trying to strip the contaminant. Another nice approach is recirculation. So in this case, you pump water out of the ground, you add your nutrients and amendments, and then you pump it back in and you create a bioactive zone. You can get very good distribution. You can add liquids or bioaugmentation cultures if you have to. But as with any pumping system, you have to put in an infrastructure. And anytime you pump water, you know, biofouling can be an issue. The last of these, or there's hybrid approaches to all of this, but there's also some in-well diffusion devices where essentially you put tubing in a well. The Waterloo emitter is one of these. It's very simple, but at least in our experience, this is, you know, the simplicity is kind of overcome by a very poor radius of influence and difficulty in controlling gas concentrations in the aquifer. So, you know, typically we've had a lot more success with the active biosparging and the groundwater recirculation approaches. Just going to give a few considerations and then move on to some, you know, just some thumbnail sketches of some field demos. But one of the things that people often forget about in doing this is you're adding carbon to an aquifer. You're adding, propane or methane or isobutane. You have to think about inorganic nutrients because bacteria require these to grow. And if you add enough carbon that you overcome what's naturally in an aquifer, you're going to reach a limitation. And this shows a very nice example of this. This was a study that we did with 1,2-dibromoethane, and I'll show this. As a field experiment. But basically, when we did microcosms, we added ethane or propane plus diammonium phosphate, or we just added ethane and propane alone, or the diammonium phosphate alone, and that's an inorganic nutrient, the diammonium phosphate. If we just added the gases, we saw no degradation of dibromoethane. If we just added the nutrient source, we saw no degradation of dibromoethane. If we added them together, so you're adding the inorganic nutrients plus the ethane or propane, we saw good rapid degradation of dibromoethane. And in the case with the ethane gas, basically the level in these microcosms was less than 20 parts per trillion at the end of the study, which is the MCL in Massachusetts where this was done. There's a 50 part per trillion national standard for dibromoethane. So nutrients are very important. The other thing that's very important is kind of taking a good look at which substrate you should use because there are many, many choices. Things like methane, ethane, propane, isobutane, they can stimulate different organisms, and some of those organisms will differentially degrade specific contaminants. So it's a good idea if you're going to apply this process to use microcosms, so you can understand which substrates are most effective. Take a look at relative rates. So how quickly do the different contaminants degrade? And a lot of times you can apply this for multiple dilute contaminants, most chlorinated solvents plus 1,4-dioxane. And there's the potential to use multiple substrates to do that. So you can work all this out in microcosms. The third thing are just looking at the properties of the gas, solubility, how much of it goes into solution, what is the LEL, because that's one of the things when you're engineering this, you don't exceed the LELs when you add these to groundwater to assure there's no issues. And purity. It's easy to go to Home Depot or any of the big box stores and buy propane in a cylinder, but that's not a grade of propane that you really want to use in a field demo typically. It has a lot of propene. It has mercaptans that inhibit, so you can smell it if it's leaking, but those can also inhibit bacterial growth. And basically in this figure, this just shows again this EV425 organism growing on 99% propane in a cylinder versus trying to grow on the propane that you get from one of the big box stores, and it doesn't grow particularly well at all on the big box store propane. So. Spend a little more. I mean, the gas is going to be a very, very low expense for any of this type of remediation. So it's worth getting a gas of higher purity. So I'm going to do really 3 short field studies, and then we'll move into a Q&A. First is on a groundwater research system for dibromoethane. The second is going to be a sparging system. And the third, I'm just going to give you a snapshot of a sustainable solar-powered biobarrier system. So this is, we're at the point with this approach where you can do it completely off the grid and still control it from your desktop in terms of your gas additions, pumping water. So there's a lot of advances that have been made in applying this in the field. Okay, let's talk a little bit about EDB. 1,2-dibromoethane, a very simple compound. It was used in leaded fuels. It's still used in avgas. And essentially, it was a lead scavenger to keep lead from plating out on engine components. It's a potent carcinogen. Interestingly, I do some work with John Wilson, and he's told me on multiple occasions, this is the compound that's given him the most concern over his career in terms of a carcinogen. It was phased out in the 80s along with leaded fuels, but it really persists at thousands of gasoline sites. I mean, the fortunate thing is that it slowly hydrolyzes with time, so the concentrations are going down, but Ron Falta did some great work about 10 years ago and basically looked at data from a variety of sites where they'd gone back to, former gasoline spill sites. And at a high percentage of those sites, EDB was still there above the MCL, but frankly, we don't look for it typically. So it's one of these things that, some contaminants, we basically throw up the alarm for, and this is one that we haven't and maybe should think about. It has a lot of the characteristics I talked about before, very soluble, doesn't sorb well, doesn't strip particularly well. There are some organisms that will grow on it, but the concentrations are often very low in aquifers. But basically, it's a very good cometabolic substrate, and there's lots of different substrates that bacteria will grow on and degrade dibromoethane. So I showed you those microcosms previously. So essentially, through some Air Force funding, we did some work up at Joint Base Cape Cod, and they currently have pump and treat systems that are treating EDB from former fuel spills. The hydrocarbons from this spill were remediated in the 90s, but you have a long plume of EDB, and when you have a low MCL, your plume is larger, right? So depending on the MCL of the compound is kind of where you often draw those plume lines. So you have some pretty large plume here with EDB. So we did a pilot test in which we did a recirc system. So there was an existing extraction well from the pump and treat system pumping like 50 GPM. We took a 10 GPM slipstream. We amended that with ethane, oxygen, and inorganic nutrients, diammonium phosphate, and I showed you that treatability work. We went about 60 meters up gradient, put in an injection well, and then injected it through the injection well. So the idea here is to create a reactive zone between the extraction well and the injection well, and to add our amendments. And we had a series of monitoring wells in between. Here's just a view. This is just the system box. But essentially, first I'm going to show you the ethane. And what we did is we just recirculated groundwater for about 3 months to try and stabilize the EDB concentrations, and I'll show you that in a minute. And then we started adding our gases. We started adding then inorganic nutrients in batch to the recirc system. But one of the things you see is we get sort of this initial hit of our gases, and you can sort of see these concentrations, and these kind of reflect the different wells along the flow path. But with time, now realize we're continuing to add these, 24/7. So we're pumping water at 10 GPM. We're adding these gases at the same basic amounts. But look, the concentrations in the aquifer are going down and down. And what's happening here is over about this 3-month period, you're growing a lot of biomass in the aquifer that's consuming that ethane to the point that you're not getting a lot of ethane. You're getting none coming into the box in the recirculation system. And you just have, by the time, we're out here about 3 months after addition, you basically have very little ethane in the groundwater at all. So my point about overcoming this competitive inhibition, well, the organisms are consuming it all. So you're not going to have a lot of competitive inhibition in the aquifer when you're applying this properly and you're building a good biomass population. Now, here are the EDB data. And again, here was this sort of period where we just recirced and realized, the concentration in this part of the aquifer is only 300 parts per trillion, or 0.3 ppb. Now, the Massachusetts MCL is 20 parts per billion, so you're still in more than an order of magnitude, about 15-fold above that. But you see, we're just sort of recircing, nothing's going on. We start adding our oxygen and ethane, we start adding our nutrients, and in all of the wells that were connected to the system, we see really good significant losses of EDB, to the point where by the time we shut it down to look at rebound, we had achieved less than 2 parts per trillion in 4 of our wells and less than 20 parts per trillion in all of the wells that were connected to the system. So all the wells where we were seeing ethane and bromide, so they were in the flow path of the system, we had achieved that, that level of contaminant treatment. You start to see rebound after you shut down. Of course, this needs to be an active process, but that rebound was a lot slower than I would have anticipated in some of these wells. And I think what was happening is the organisms were continuing to grow on biomass that was in the aquifer and continuing to degrade the EDB. Now, I'll just point out that this line here, this is actually the water that was coming through the box. So this was from a 50 GPM pumping well that was pulling in a large zone of influence, and we were just taking a little slipstream. But you can see the concentration of that, which had been steady for many years, it declined in this area. So we were impacting that entire area that this large well was drawing from in terms of its concentration. All right, second, again, short case study. This was a project at Vandenberg Air Force Base looking at the treatment of 1,4-dioxane. but also, low levels of CVOCs that occurred here. This was called Site 24. It was a tank maintenance site. There's a whole webinar on this project that you can take another look at. But just in general, we all know a lot about 1,4-D. Pretty much everyone has a site somewhere that has 1,4-dioxane. It's a stabilizer in trichloroethane. So it commonly occurs at sites that have TCA, as well as many, many TCE sites. It's soluble, low KOW, low Henry's law. There are organisms that grow on 1,4-dioxane. Aerobically, there's none that will grow on it anaerobically, but it also can be treated cometabolically. There's lots of different bacteria that can grow on things like propane, ethane, isobutane, and cometabolically break down 1,4-D. Now, the site, this is just a little bit of the lithology. There were sort of three zones here, a shallow, an intermediate, and a deep zone. And this demonstration, and this was led by Rob Steffen and Dave Lippincott at Aptum. I guess it was CB&I in those days. But essentially, I put in one sparge well, a series of monitoring wells, and worked in this deep zone where you had, some good sands and you could get a good radius of influence through sparging. There was an existing well, this is 5B, which was screened over a very broad interval. I'll talk about this well a little bit, but it was probably bringing water in above the zone where the gases were being added. And there was a control well, which was further up in the aquifer, screened between the shallow and intermediate zone. So the idea here is you have one sparge well, you're sparging in propane and oxygen, you're adding some inorganic nutrients, and you're looking for 1,4-D and VOC degradation throughout this zone. Little bit, so 28 days, there was just oxygen added, about 10 SCFM, added propane addition, and some microcosms showed that there weren't a lot of propanotrophs down in this zone. So there was also a bioaugmentation performed right down the basically the sparging well. Began propane addition around day 29, and then as you got into sort of a routine and looked at the how quickly your gases were degrading, basically it came down to adding about 6 cycles per day. Again, this was all on a SCADA system, so you can inject right from your desk, and then periodic nutrient addition. So you're basically adding propane and oxygen in 6 cycles per day, and you're periodically, monthly adding some inorganic nutrients to this area. Here are the data. So this was sort of pre-addition. This was in that oxygen, just oxygen sparging phase. You see no losses of 1,4-dioxane, and see you have concentrations here from about 100 to 1,000 ppb or 1,100 ppb in the aquifer. And then here's the beginning of propane sparging and then bioaugmentation. And what you see over a period of a few months, again, in all these wells that are well connected to the system, you're getting greater than 95% removal of 1,4-dioxane. And for 3 of the wells, you're getting, down into the 1 ppb range and greater than 99% removal. This is the control well 5A. There was no influence there. And this was that broadly screened well that I talked about. That was a pre-existing well that was sampled. There was not very much propane observed in this well, and it's very likely that it was just pulling water above the formation from where the demonstration was being implemented. So, but again, this worked extremely well for 1,4-dioxane. And there were low levels of VOCs in the aquifer, TCA and DCE, which is a hydrolysis product of TCA, as well as some TCE. And initially, this kind of the real focus here was 1,4-dioxane, but of course, in running analysis, VOCs were also analyzed. And again, in all of these wells, and there were really pretty low concentrations, TCA up to 10 ppb, DCE up to a little over 100. At least, again, these are the wells that were sort of right within the influence of the propane zone. This again is that, and this also indicates that 5B well was pulling from a different part of the formation. Concentrations are much higher and didn't change very much over time, as with 1,4-dioxane. But there was degradation of TCA, DCE, and TCE down to below detection in all of these wells that received propane. So the question came up, well, was this just stripping? These are pretty low concentrations, you're sparging. So water was collected from some of these wells, came back to the laboratory, our lab in this case, and we added propane to some of those. and added acetylene to others to try and inhibit, that's basically an inhibitor of this type of activity. And biodegradation was documented of each of these chlorinated solvents when propane was added. So while there may be some stripping, as part of this, certainly biodegradation, cometabolic biodegradation was a major component of degrading these chlorinated solvents. And I'll mention some other work that was ESTCP funded by Jacob Chu and Hunter Anderson and others, where they used propane in a recirc system at a site, and again degraded 1,4-dioxane and a bunch of chlorinated solvents. So this was repeated at a couple of different sites at a good size field scale by different processes for adding gases to the ground. Now this is my last slide before we move to Q&A. And this is a sustainable solar-powered biobarrier. This is an ESTCP-funded project that's led by Dave Lippincott. And this was the topic of the webinar number 128. So I'm just showing one slide, but if you want all of the details in about 20 minutes, you can go look at webinar 128, which is online on the Certip ESTCP website. And this is a great little system. This is a solar-powered biosparge system. So we see solar panels. Here's a Connex box. There's a computer in there and different lines to move out to a series of gas sparging wells. And what you can't see here, because everything is flush mounted, there's about a 220-foot biobarrier here with sparge wells on 15-foot centers. And essentially what happens here is the system automatically adds propane, oxygen, and ammonia gas as an inorganic nutrient or a nitrogen source with nitrogen in between each of those, and it sparges into the aquifer on cycles. And you can control, again, through a SCADA from your desktop, how often those cycles are implemented, what the concentrations are going into the aquifer. And in this case, this was at former Myrtle Beach Air Force Base. There's actually a runway off to the left of here for the Myrtle Beach Airport. But this had cis-DCE and vinyl chloride above MCLs, and that was from some former anaerobic treatment at the site. But again, what you have is, you have this sort of dilute plume that remains, and very likely, as at many of these sites, what you have are some solvents that are caught up in clay layers or low permeability formations that continue to leach out over time and kind of sustain these dilute plumes. So, here's an approach to look at that, an off-the-grid barrier. And just with cis-DCE, there were concentrations from about 20 to 100 ppb. You see this is just sort of background addition, no changes. You start adding propane and monitoring concentrations, and it takes about 3 months to start growing that biomass up. So what was done here is you measure propane in the aquifer over time, and finally, as you see it start to degrade, you start adding more. These are just different cycles. And what do you see is the biomass starts to build up. You start to see losses of cis-DCE. And you see the cycles are getting a little closer together because the organisms are consuming all of the propane. And then you reach a point where, you're non-detect in many of the wells and there's some, low concentrations in others, but the MCL here was met throughout this whole treatment zone. And it's fairly high. I think it's 70 for cis-DCE. But there was non-detect levels in many of these wells. And there's always that one well that, you always put in one well too many at these demonstrations, or there's one that you always have to explain. But there was one here that didn't respond quite as well. But that's the reality of everything at times. But again, overall, this worked great for cis-DCE, and it basically, in again 7 of 8 wells, MCLs were met, and that's 2 parts per trillion for vinyl chloride from levels between again 5 and almost 30 parts per billion. So. The system worked really well. It's an off-the-grid system. I think I just wanted to show you how far this is advanced in terms of doing this in the field. And from there, we'll move into Q&A session.
Great. Thank you so much, Paul. We did get a lot of questions. The first one is from the Air Force Research Lab. How is microbial growth measured in your experiments? And is active microbial growth correlated with higher degradation rates?
Both excellent questions. So, as many do, we look at different organisms through qPCR, so looking at different gene targets. And there are different companies, Microbial Insights is one that offers a package where you can look at many of the different cometabolic genes of interest. And in some of these demonstrations, you see large increases in populations. So the answer is yes, that it's very important to grow these organisms. And as the density gets higher, your degradation rates get much better. So it's, that's just like traditional growth link kinetics, you really do have to grow the biomass. The one caveat here is that a lot of these organisms tend to absorb well in soils. So if you're just pulling groundwater samples, sometimes you will see excellent performance, but you won't see a lot of increases in the presumed population. And I think when that does happen, what you're really seeing is you're getting great growth of these populations, but they're absorbed as sediment. So unless you're willing to go out and take some core samples, sometimes you can scratch your head a little bit about the microbial data, but I think it's just because they're not planktonic sometimes. They're not in the groundwater, they're absorbed to the sediments.
Great, thank you so much, Paul. This next question is from the Arizona Department of Environmental Quality. Arid environment aquifers with very low dissolved organic carbon have extremely low native microbial cell densities. Is there a minimum native population density that you look for to initially guide you in making a decision of whether to go the biostimulation route or the bioaugmentation route when planning feasibility studies?
Yeah, that's a really, really good question. And that's where I kind of yield to microcosms in that case. Again, because if you're sampling groundwater, sometimes I don't know how indicative that is of the presence of these organisms. With microcosms, and you kind of have to go out and get sediments as well as groundwater. But as you start to add the gases, you'll typically see whether you're going to get growth or not. And in most cases, even in some of these very oligotrophic aquifers, you would be surprised that these organisms are there. You can try different substrates. And a really good example of that was that Cape Cod study that I showed for EDB. That's a very pristine aquifer. That's a very low carbon aquifer. There's no nitrate. There's no, very low nutrient sources. It's kind of, probably somewhat like you have in Arizona. That's a classic, very oligotrophic aquifer. And yet, by adding nutrients and ethane in that case, we were able to stimulate a population. We didn't have to bioaugment. And, essentially, I showed you those data, had very, very good results in the field. But, I would yield to results of a microcosm study in that case. And there are bioaugmentation cultures available, but anytime that you can use biostimulation, I think do that preferentially, because it's always better, I think, to stimulate the native populations when you can for cometabolism.
Thank you, Paul. This is a question from the University of Cincinnati. Do you add gases at a constant rate or periodically over time?
Yep, another great question. It depends on the application. So in the sparging application, we usually do it periodically over time. So a lot of times, what you do is you start adding your gas, and then you measure its concentration in some local wells. So if you're adding, let's say you're adding propane to an aquifer, you measure over time, and as you see that propane get consumed, then you add a second time. And what you'll often find is as you stimulate the communities to grow, that addition rate has got to be more and more frequent. So you may go from adding once a month over the first couple of months sometimes, to then suddenly weekly, to several times a day. And the idea is to grow up that population to feed it, but to ultimately keep your gas concentration as low as you can for as long a period of time as you can, because that's when you're degrading, particularly for VOCs, at the most rapid rate. So when these organisms are well induced, the enzymes are active, but there's not a whole ton of your primary substrate around. In a research system, sometimes you can add continually, which is what we did up on Cape Cod. And again, it's sort of a matter of monitoring. So is that gas being consumed? If you're starting to see a buildup, that usually means either the population isn't large enough yet and you can back off on the concentration you're adding, or you have some other limitation. And as I mentioned, inorganic nutrients are critical in these applications. So you need to think about a gaseous or a liquid, particularly a nitrogen source.
Thank you, Paul. Here's a question from Raytheon. And the question is as follows. Have there been any longitudinal studies of how microbial ecology community structures change over the course of treatment?
Yeah, good. Not that I'm aware of. Typically what people will do here, almost universally, is you take a background, you take background samples, and usually they're water samples, and you look at different cometabolic genes, and then as you start adding your gas, you sort of take those same samples over a period of time. People rarely take cores, which I think we're missing a lot of information by not doing that, but it's very expensive. It's not cheap. If everything is working well, then that population has come up and done well. Um, if it's not, then there's a whole variety of things that you need to think about. But in terms of the microbial communities, we're at a day now where you could pull these samples and just do next generation sequencing and see everything that's gone on. But I'm not familiar with a cometabolic project where anyone's gone out and done that, particularly looking at during gas addition, and then for days or months or years after addition. That would be a really interesting study to sort of see what happens.
Thank you. A question from the Los Alamos National Lab. Have you observed cases where cometabolism slows over time, not due to lowering contaminant concentrations or limitations in nutrients, but rather due to an evolution of the community to organisms that grow on the primary substrates but do not cometabolize the contaminants of interest?
Good question. I haven't, and typically the one thing that's pretty interesting, although not universal, but for most of the substrates you use, so let's say something like propane, there are organisms have a couple of different enzymes that they use to break down propane. One is propane monooxygenase. That doesn't actually degrade a lot of different contaminants. Maybe NDMA is one. But most of the organisms have a second enzyme called short chain alkane monooxygenase, or SCAM, which is the enzyme that basically breaks down most of the contaminants. And this is some work particularly of Mike Hyman's, who's been at NC State. Now, there could be a scenario where if you had organisms that took over that only had propane monooxygenase and not SCAM, then I could certainly see that happening. So have we ever experienced it in the field? We haven't. And I think what happens is that as long as you've stimulated the right activity, those organisms suddenly become dominant because now they're the largest population. They're consumed, they have the highest growth rate, and they have the enzyme to break down the contaminants. So if everything is working well, then that's kind of the dominant community, and I'd be surprised if they got displaced. I'll give you one example that's kind of the opposite of that, which is we had done some ex situ work, and this was a bioreactor, a good-sized bioreactor that was treating NDMA out at White Sands, and we had inoculated an organism into that reactor. We were feeding it propane, and it was biodegrading NDMA. And as we did community analysis over a period of about a year, the organism that we bioaugmented disappeared completely, and it was displaced by natural organisms from the White Sands aquifer that had the same enzymes, the same general enzymes, which were probably the short chain alkane or propane monooxygenase, and was degrading the contaminant. So the population totally shifted like you suggested, but the activity continued in that case. So that's a good question, and that's one that you could have a long discussion about.
Great, thank you, Paul. In the interest of time, we're going to have you try and finish your presentation in the next 15 minutes, but no more than 20 minutes. That way we can get to answer some of the other questions that are coming through. And I would encourage our audience members to reach out to you directly if there's any unanswered questions. But let's turn it back to you to wrap up, Paul.
Great, thanks a lot, Rula, and thanks everyone for the questions. And I'm available by email or phone anytime to answer these a little bit further. So in the next 15 or so minutes, I want to ask: are we missing a significant component of natural attenuation, particularly of chlorinated solvents, that being cometabolism? So again, going back to this dilute plume problem, you know, we now have a lot of plumes that are low concentrations over large areas, are sustained by TCE and other things that are diffusing out of clays and tight permeability formations. It's hard to implement active approaches. M&A makes the most sense, but our focus over the past 25 years has really been dehalogenation, reductive treatment. You know, we don't have a paradigm for aerobic treatment of solvents at all. So how can you implement M&A? And this is mirrored. This was Perry McCarty, 1997, at a meeting, and basically what he says here in a nutshell is that, yeah, we understand reductive dechlorination, and this is really important for transformation of chlorinated solvents. And when he was asked about cometabolism of TCE, and again, this is 1997, he said, well, you know, you need a lot of DO, you need an electron donor like methane or phenol present, and these are just unlikely circumstances in most aquifers. So aerobic cometabolism is probably of little significance for basically, you know, treatment of TCE or M&A or natural attenuation of TCE in aquifers. And I think, you know, I think most of us probably believe that then. We probably believe that now. But what I'm going to sort of show you is that that might be changing. You know, just a little further on the left here, reductive dechlorination. We know a lot about this, right? We can build a case for M&A. We have all the tools to do that. EPA buys into this. We know the organisms. We understand the substrates, the products. We can analyze for the key genes. We have CSIA. But if you start looking at the same thing for aerobic cometabolism, there's some questions here. What, you know, we need oxygen. How much? Do we know the key organisms? Are they there? The enzymes, the genes? What substrates are important? Is it just methane and ethene? Are there any unique degradation products that we can look for? CSIA is not quite as effective with this because you get less fractionation. So can we build a case for M&A? You know, what do we know about this since, say, you know, what Perry said in 1997? Has anything changed? And I'm going to say that it has. And, you know, we're going to start with thinking about the genes themselves. Something needs to turn these genes on, right? So if it's presumably if you have a methanotroph, you need methane. If you have an organism that oxidizes toluene, you need toluene. But you know, Rob Steffen, you probably can't see that paper, but this goes back a number of years, and Rob Steffen and his group was the first to show that the contaminants themselves can induce some of these oxygenases. So think about that. So you don't necessarily need toluene. You can actually have contaminants. Things like TCE can induce the enzyme to be made and produced. So that's pretty interesting, right? So you don't necessarily need, you know, the specific primary substrate to be there. And secondly, you know, do these substrates have to be these things we know about? Do you need toluene, or do you need phenol, or do you need, you know, methane or ethane? And this was actually a Nature paper of only 4 years ago. So it shows you kind of how new and important this is. This group of scientists, they took some plant root exudates, things that are commonly released into the environment. These are, you know, p-hydroxybenzoic acid and some of these other things that plants make. And they enriched organisms aerobically that grow on these, and then they added cis-DCE. And guess what? Depending on these different substrates, all of the enrichment cultures degraded cis-DCE. Presumably there's enzymes induced here that are cometabolic. They're probably toluene, mono, and dioxygenases, but they're induced by natural substrates that you find in plants. So this is occurring in nature, and these organisms are induced and active. So what other substrates might be out there that we're not thinking about? Perry said, oh, you're going to have phenol or toluene. Well, we know we get ethene and ethane when we have reductive dechlorination. Methane's common. What about soluble metabolites from fuels as they break down? Carbon release from cell death, right? We've added, we add these high concentrations of substrates for reductive dehalogenation. What happens to the cells afterwards? Well, they die and some of that moves down gradient. Past remediation, what happens to all of the carbon when you add soybean oil to an aquifer? Mentioned root exudates, landfill leachates. And the question came up about aquifers that are very oligotrophic, but on average, there's a lot of humic and fulvic acids that are around, and there's a lot of dissolved organic carbon in aquifers. This was a 1974 USGS study, but there's about a ppm on average of DOC in aquifers and ranges from about 0.1 to 15. So there is carbon out there in the world that maybe can stimulate these processes. How about the organisms? Are they around? Well, we never looked for them in the past, right? We've looked for Dihalococoides now for 25 years. But it turns out that, and in particular, Microbial Insights put a package out years ago called Quantarray Chlor. So often what people will do is they're really interested in the reductive dehalogenase genes, but as part of that package, you also get aerobic cometabolic genes. So Microbial Insights keeps a database of all this, and in some cases they have more than 7,000 water samples now. And I asked Dora Taggart if I could take a look at some of these genes. And look at that. This is phenyl hydrolase. These are two toluene monooxygenases, methane monooxygenase, and a toluene dioxygenase. So in the samples they've looked at, these genes are present from between about 40 and in about between 40 and 80% of samples. That's a lot, right? Because you're not, these are probably mostly sites where you're doing reductive dehalogenation, yet you've got a high presence of these different genes that are, have cometabolic potential. Now, we go a little further into that. This was some work of Certip work from Tim Mattis, and they basically went out, his group at Iowa and others went out and basically took a look at just the co-occurrence of aerobes and anaerobes, basically. So Dihalococoides and organisms that could aerobically degrade vinyl chloride, that basically the genes were found together in almost every sample, strict aerobes, strict anaerobes, and they were expressed in 60% of those samples. So these organisms are out there and they're kind of living together. And this paradigm we all have, right? Anyone who's taken an environmental course that has to do with, treatment or remediation or a fuel spill, you see this, right? And you have this big fuel spill, you get a lot of carbon in an aquifer, you consume all the oxygen, then the nitrate, then the iron, then the sulfate, and methanogenic. And we kind of all have this picture in our mind that segments all these processes. Oh, this is sulfate reduction here, this is aerobic respiration here. But I'm going to argue that that's really not the case. And in fact, what we have is a world of niches. And particularly these days in these dilute plumes, I think a lot of these niches revolve around clays and formations that are, very tight, where maybe you have TCE held up, you have reducing conditions, you're getting methane. But the bulk aquifer, this is my clay, and this is sort of your sandy aquifer around it that maybe has some oxygen. So what's actually happening at these interfaces, where you probably have low oxygen, maybe you get some TCE diffusing out, you have methane around, or you have some other organic material, are you getting cometabolic processes occurring here? And even if, let's say this aquifer only has half a ppm of oxygen, what's sufficient? And there was a great paper by Jim Gossett more than 10 years ago, and he did something that people don't typically do, which is, he put some little tubes in cultures as well as in some microcosms, and he added a really low flux of dissolved oxygen. And basically, if he could add 20 parts per billion of DO into solution, right, he was getting the continuation of aerobic vinyl chloride degradation. If he did that with cultures, if he did the same thing with microcosms, having only 100 ppb of oxygen in a sample allowed these processes to continue. Now, when you go out in the field and you're measuring DO with a meter, once you get below a ppm or a half a ppm at the most, we consider that, anaerobic, anoxic. Those processes aren't going to occur. And I think that's dead wrong. I think really what we're looking at is a flux of oxygen, and very low levels can have a very big impact. And I just want to mention a project as I move through. And one of the problems is we rely on wells for everything. And when you're in a well, you're basically pulling most of your water from a conductive sand interval. And if you have clays and mixed layers, you're not really seeing what's going on in any of those. So there's some movement afoot. We've done, passive sampling in sediments for years, and Andrew Jackson at Texas Tech has a project where he's developed these direct drive passive samplers, and they have little compartments. So you can basically equilibrate water in sands, in silts, in clay layers, and then you pull these back out and you pull water samples out, and you can look at microbial communities, you can look at geochemistry through cations and anions. So it kind of allows you to start differentiating these communities and processes in a very heterogeneous aquifer. And I think this is important in our ability to understand what's really going on in some of these aquifers and to get away from wells a little bit. Okay, so one of the other difficulties in documenting aerobic cometabolism is you don't have daughter products that are kind of typical, right? So the great thing is you degrade TCE, you're not producing cis-DCE or vinyl chloride, but that's what we look for to document TCE degradation. So if we go aerobically, you go through this epoxide and then you break down to things like formate, which is readily aerobically degradable, glyoxylic acid, which is degradable, dichloroacetic acid, and ultimately you end up with carbon dioxide. We really don't or can't look for any of these in an aquifer as evidence of natural attenuation. You sort of can't look for CO2 easily. So, is there any way to detect this? And there was kind of what I would consider a major breakthrough or a revisitation of kind of an old technique. And this was part of an ESTCP project led by John Wilson with a lot of collaborators. And they were looking at both potential for cometabolic activity at TCE sites as well as sort of mineral reactions. So I'm just going to kind of focus on the cometabolic part of it. But essentially, David Friedman down at Clemson and some of his students basically developed an assay where they ultra-purified radio-labeled TCE. So they pass it through a gas chromatograph to take out any impurities, and then they inject it into bottles where they've, in this case, collected groundwater from sites around the country. And if you go back 15 years, why would anyone even do this? You basically have these aerobic sites. You don't think TCE is going away, right? There's no evidence of that. So this is a way to very sensitively see if anything is going on. So what they do is they get groundwater as fresh as possible. They put it in bottles. They add radio-labeled TCE that's ultra-purified so that doesn't have contaminants. And if there's any active aerobic cultures in there, they'll degrade that to soluble products and CO2. So what you can do then over time, you can pull samples. If you add base to those samples, all of your CO2 becomes carbonate. So you can sparge it, and you can get rid of any residual TCE, but you've got your soluble products, which don't sparge out, and you've got your carbonate now, which won't sparge out. So you have your combined products that are produced. If you add a little barium chloride to that, you precipitate out your carbonate as barium carbonate. You can centrifuge that out, and then you just have soluble products remaining. So with this assay, what you can do is you can grab samples, you add this ultra-purified TCE, and then you can look at how much radioactivity is present in the carbon dioxide and the soluble products. And over a function of time, you can then calculate a degradation rate. And those rates, with this assay, you can get to something on the order of half-lives of 100 years. Okay, so here are the 5 sites they looked at, and this has been published now, so you can get the paper from David. But basically, in 3 out of those 5 sites, there was clear cometabolic activity with half-lives of 0.3 to 107 years. When I saw this data a number of years ago, it was one of the most interesting things I'd seen in a long time, and realized this is just with groundwater. So 3 out of the 5 sites, you had cometabolic aerobic degradation of TCE, and here are the products. A lot of it's going to CO2. So I think this assay is sort of a game changer to start looking at aerobic natural attenuation of things like TCE. This was a project that I'm a PI on, and what we were interested in here is basically looking at degradation at low pH. And I had talked to David Friedman, gone down to his lab, and we had a chat and decided to collaborate on this. And basically what he did here, one of his students did, Anthony Swast, is We went down and collected samples from this little site in Maryland. It's a TCE plume. They installed a big mulch biobarrier to try and treat this anaerobically, but the groundwater pH is really low, and it's about 4.5. And essentially, you get flow through this barrier, and you get TCE. You get some good, decent degradation in the barrier, but you get cis DCE coming through, which is common at low pH. So what we did is collected samples from this up gradient well within the barrier and down gradient, and set up the same assay. So this is a lot of work. And Anthony's student set up an assay where he just added soil and groundwater, or plus methane and nutrients, and looked at half-lives of TCE aerobically. Now this is an anaerobic barrier, but looking at aerobic half-lives. And essentially, if you went up gradient here, even at a pH of 4.6, you added a bit of methane, you see enhanced degradation. You add methane and nutrients, you see much enhanced degradation of TCE aerobically. So the half-life is about 2 years. If you get within and downgrading to this barrier, you've got half-lives of well under a year. Now, this is an anaerobic treatment process, but there's aerobic cometabolic processes presumably going on at the same time. And I think we miss all of that when we're looking at a lot of these anaerobic sites. And I think it's an important contributor to losses of some of these contaminants. So I'm just going to finish with a couple of slides, because there's a lot of people out there who are always interested in 1,4-dioxane. And this was some work a few years ago by Dave Adamson and Chuck Newell at GSI, along with Hunter Anderson, Shaylee Mahendra, UCLA. And basically just they looked at Air Force sites, and they looked at flow models and 1,4-dioxane and calculated some half-lives. And for about 50% of the plumes that they looked at, or wells that they looked at, half-lives were less than 4 years. So 1,4-dioxane apparently is degrading somehow. And there was a positive correlation with DO and a negative correlation with metals and VOCs. So that positive correlation with DO to me suggests this is a biological process. It suggested the same thing to them. Could be growth linked, could be cometabolic. But how do you look further? Well, again, Friedman's group, under the leadership of Tony Danko, and in collaboration with Carmen Lebron and John Wilson and Dave Friedman and others, they sort of converted this 14C TCE assay to a 14C 1,4-dioxane assay. So again, they can see dioxane being broken down using ultra-purified radiolabel. And this took some ingenuity, because you can't sparge out 1,4-dioxane. So what they've done is they've acidified and sparged out CO2. So they've developed a whole system to be able to do this and look at 1,4-D products. And there's 2 new papers in Journal of Hazardous Materials in late 2021, early 2022 that will show some of these results. But again, what's most important, they've gone to 10 sites, collected 54 groundwater samples, and in about 45% of the wells, they're seeing evidence of 1,4-dioxane degradation. Half-lives of about 2 years to 328 years. So some of these processes appear to be fairly slow. But again, you're just looking at water in this case. You're not looking at any of the sediment, so there could be, some faster rates in the field. But again, it shows the potential for this. And you see kind of this L-shaped curve. The other thing is sort of interesting. 1,1-DCE tends to be problematic at high concentrations for cometabolic processes, I guess, as well as metabolic for 1,4-D. So you see these rates of 1,4-D degradation when there's no solvents, and then they get a little slower potentially as you move along. But the important thing is that this assay is developed now to take a look at this. It's really, I think, novel and interesting work. So I'm wrapping up right now. In terms of the M&A, I think cometabolism is playing an important role. We have new tools to start quantifying this, including this 14C assay, as well as some gene probes. You're going to need a multiple lines of evidence approach, but I think in the future there could be some guidance akin to what we have for M&A for anaerobic environments, and this could be really important for dilute plumes of VOCs and potentially 1,4-dioxane. Conclusions overall, what's really important here is this field has really progressed. We know a lot more about these organisms. They're a lot more complex and interesting than we thought. This cometabolic treatment has a lot of potential for dilute plumes at DoD sites and really should be used a lot more frequently. You can achieve low concentrations sometimes. And I already talked about the M&A as maybe being completely unrecognized and yet potentially very important. DoD benefits. I think, there should be a lot more applications of this. I would love to see that. It's very applicable in the field right now. It's been vetted in a lot of ESTCP field studies by our group and many others. And, there's a potential big cost savings to apply this compared to pump and treat in particular. A lot of people contribute to these projects, and I try to highlight, work from a variety of others as well as our own group, and certainly wish to thank Certip and ESTCP for funding a vast majority of this work along with AFCEC and DoD. There are references, but please, if there's anything you want to look at a little bit further, shoot me an email. I'll be happy to send you a paper or point you in the right direction or tell you who you should sort of talk to.
Thank
Additional
you so
information,
much, Paul.
and thanks, Rula.
Oh, yeah, maybe you can leave the slide up with your contact information, and that way we can go ahead and have people whose questions are not answered now reach out to you. And then, of course, this is your project webpage where your training materials and your final report will be posted, and everything on this web link is free of charge. All right, well, let's get into the questions. For your carbon-14 assay for TCE, can you let us know if that is available commercially, Paul?
Actually, it is. Yep, that's right. That was, an assay David Friedman developed, and he has a relationship, is my understanding, with Microbial Insights. So you can go to Microbial Insights, and they will be able to run that assay for you for TCE. I'm not sure if it's available for 1,4-dioxane, but it's definitely available for TCE.
Great, thank you. This is a second question from Raytheon. Are there other alternative primary metabolites besides alkanes that could enhance cometabolism, even if they aren't ideal from a practical engineering perspective, things like fatty acid esters?
Yeah, so that's a good question, and that's kind of the holy grail. So if someone can develop a substrate that is soluble in water, that's not a gas, that preferentially stimulates these cometabolic enzymes, that's a really big advance. I think, as I showed in some of the M&A stuff, I think there are a lot of natural compounds that can stimulate these processes, but they're not specific enough to try and use them in the field. I'll say that one of the things that we're trying currently at a site to grow populations is using isobutanol. So there are a lot of organisms that grow on isobutane and biodegrade different types of contaminants of concern. So what we've been trying to do is we did a bioaugmentation, and this is at Naval Air Station North Island. We did a bioaugmentation, and we're adding isobutanol to try and grow the population without really inducing the enzyme that degrades the contaminants, because what we have there is a toxicity issue. We have super high levels of 1,1-DCE, and if we start adding just isobutane, we have ppm levels of that, which is fairly high, then the organisms seem to be dying off. So by adding isobutanol, we're trying to stimulate the population preferentially, and then we're adding the isobutane gas to turn all those genes on and degrade the chlorinated solvents. But to my knowledge, the problem is sort of non-specific growth on a lot of these substrates. So the question that came up earlier, maybe from you guys also, but is, do you see activity sort of die off? And when you add these substrates that are really not that specific for the oxygenases, then I think you run a high potential of not stimulating the right organisms.
Great, thank you so much, Paul. All right, this next question is from Langen. Commercial labs offer a limited number of identified monooxygenases. When and how do we search for these enzymes, say for 1,4-dioxane at very low concentrations?
Mm-hmm. Yeah, the the one thing that I sort of didn't mention from the 1,4-dioxane work that I sort of showed a couple of those slides quickly at the end. That's, Tony Danko and Dave Adamson and Dave Friedman, John Wilson, a lot of folks, Carmen LeBron, is that when they went out and tried to look for some of the cometabolic targets at sites where they had low levels of 1,4-dioxane, there wasn't a very good correlation between any of those cometabolic targets. And you're looking at things like for 1,4-D, you're looking at things like tetrahydrofuran monooxygenase. You can look at some of the toluene oxygenases. Methane monooxygenase is not very relevant because, methanotrophs don't degrade 1,4-dioxane. But they didn't see a very good correlation. So some of the sites where they ran the C14 assay and had decent rates, they didn't see corresponding good levels of some of these gene targets. So, there's a couple of reasons for that potentially. One is, again, you've got absorption of these organisms to sediments, and we're always looking at groundwater. And the second, the second situation might be that maybe we're not looking at the right, maybe we're not looking necessarily at the right gene targets. Maybe we don't know yet. Maybe there are others that we haven't come across. But you have a suite of those that are offered by some companies like Microbial Insights, and some of those, are targets for 1,4-dioxane. But the point being that that's kind of a tough situation, and I don't know necessarily that you can go out and run a gene assay and come back and say, yeah, there's going to be activity here or not. I don't know that the correlations are very good. I think the C14 assay with 1,4-D is probably going to give you more information.
All right, Paul, we have time for one more question, but we got about 6 questions that talk about potential limitations from a contaminant or field condition perspective. So I'm going to ask you a general question that if you can answer it in 2 minutes, that would be great. Are there any CVOCs where cometabolism will not work for as a remedy, or any conditions where practitioners should be cautious in attempting cometabolism, like low pH, for example?
Yeah, absolutely. So again, what I tried to focus on here throughout the talk were low concentration plumes, again, where you have ppb or maybe a few hundred ppb of different contaminants. As you start to get into higher concentrations, ppm levels of chlorinated solvents in particular, this is not necessarily a good approach because you form toxic intermediates, particularly with chlorinated ethenes like TCE. 1,1-DCE in particular is a very problematic compound when you start to get high levels of it. So this is a very difficult approach to, and really not the right fit for ppm concentrations of chlorinated solvents. So that's something to stay away from. Other contaminants that, or VOCs that it won't work for, it's not a good option for PCE, the perchloroethene, under any circumstances. There were a few papers years ago, and there are a few people who run around and say, it's co-metabolized, but there's really no good evidence that PCE is a co-metabolic target. Carbon tet's another one that is a significant challenge for co-metabolic type approaches. Very anaerobic sites, you need to be able to make things aerobic, and that can be a real challenge. If you have very, very low ORP, even though the organisms might still be there, as I showed, there's that sort of cats and dogs scenario that even if you have very low ORPs, you have to be able to get enough oxygen into the aquifer to stimulate the process. So that's another scenario. I think the sweet spot is lower concentrations. It's low mixed concentrations, and there's very few other approaches for that scenario, which is kind of why I think this is the target for that. It's not a high concentration technology for chlorinated solvents. You can degrade higher concentrations of some of the co-contaminants, things like trichloropropane or 1,4-dioxane, because there's no toxicity issues typically associated with aerobic degradation of those. But frankly, those are some of the limitations, I think.
Great.
The other project, just to finish up, I mean, low pH has always been a problem in terms of reductive dehalogenation, just because once you get, below a certain pH, the organisms that partially degrade chlorinated solvents tend to thrive, and Dihalococoides does not. So you get partial conversion often to cis-DCE, and that's one of the cis-DCE stall reasons. And we've been doing a lot of work looking at methanotrophs at low pH, and it turns out a lot of those are active, and in fact they can degrade TCE at we've got some examples of pHs in the 3s where methanotrophs can degrade TCE.
Thank you so much, Paul.
Okay, thank you.
Really informative webinar. We do have to wrap up, so we encourage you to reach out to Paul for additional responses to your questions. I would like to wrap up by reminding everyone that the next webinar is in the series is on Thursday, February 10. It will feature DoD-funded research to understand and quantify the abiotic degradation of chlorinated solvents in groundwater. You heard Paul refer to Dr. David Friedman at Clemson University. David is going to be one of the speakers, and he'll discuss the development of a lab protocol using a carbon-14 assay to quantify degradation rate constants of CDOCs based on the accumulation of daughter products. The webinar will also feature Dr. Dimin Fan from Geosyntac Consultants, and Dimin will talk about the development of a field kit capable of measuring the oxidation reduction potential of aquifer sediments in situ. As Andrea mentioned, registration is open for this and the remainder of the webinars in 2022, so please feel free to go in and register for these webinars. I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the brief survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.